Hi, good morning, friends. Today, in our chemistry class, we are going to discuss about Bohr model of atom. Right? We have come across the idea of atom and the particles which constitute an atom, etc. We have already come across, and some atomic models also we have gone through in the previous portions of the chapter. Structure of atom. Right? Now we are entering into a model of atom called Bohr model that was developed by a Danish scientist Niels Bohr. He actually played a big role in quantum mechanics. This is the first quantum model of atom, we can say. It is called Bohr model of atom, and it was during the beginning of the 20th century. Right? So we are going into the details. Sometimes we call it as planetary model. Actually, planetary model, Rutherford model also can be called a planetary model, but usually we refer this to planetary model because as sun at the center and the and Earth and the other planets revolving around the sun in their orbits that we know. A similar picture is used in the case of atom also. Nucleus is at the center. It contains two types of particles, protons and neutrons, and electrons, the lighter particles. That also you know, they revolve around the nucleus. That is the basic picture. So before going into the details of that picture, I will show the slides and let me enlarge the slides before we go into the details. Okay, fine. So this is our Danish scientist Niels Bohr, who developed in 1930. Before going into the details, we briefly go through the three particles. We call them fundamental particles, but nowadays we know the particle physics has advanced, and proton and neutron are not truly fundamental particles. They are made up of quarks. You may be studying it in the physics class, but as far as we consider the structure in the chemistry point of view, we can consider these as fundamental particles: electron, proton, and neutron. Right? Absolute charge in coulombs, it is for electron it is negative 1.6 into 10 raised to minus 19 coulombs. For proton it is positive 1.6 into 10 raised to minus 19 coulombs. Neutron is chargeless, we know. Relative charge, that in the atomic scale we consider electron is having 1 unit of charge, proton is also having 1 unit of charge, one is negative and one is positive. That's it, neutron 0. Okay, when you come to mass, we know these electrons are having very less mass compared to proton or neutron. Proton and neutron have almost equal mass, 1.67 into 10 raised to minus 27 kilograms. And the last digits, there will be some difference. While this electron is having a charge of mass of 9.1 into 10 raised to minus 31 kilograms. So that is it. Now, in atomic units, unified mass, atomic units, we can see that proton and neutron almost equal. There is some difference, and electron is having very less. In actual figure, it is so. So we approximate it as like electron is having zero mass, proton is having mass of 1 unit, and neutron is also having a mass of 1 unit. That's also an approximation. If exactly the values are given like this, 1.00727. That is the mass for relative mass, or what you call the unified mass in atomic scale. In kilograms, we have other units. So just revising that, remembering again. So proton and neutron are the particles which have mass. Electron is almost massless, and all the mass is concentrated at the nucleus. That we have studied in Rutherford model actually. And I'm not going into the details of Rutherford model or Rutherford experiment now, because we have already done that. Now, one point I want to emphasize, there were some defects or demerits for this Rutherford model. There were, when it was not in agreement with some experimental facts. I'm not going into that details also. But one point that was specially noted by Niels Bohr was that these atoms, when excited either by heating or by giving electricity, high temperature, heat to high temperature or discharge, electric discharge is done, we can have light emitted from atoms. So barium, potassium, sodium, calcium, vapor lamps are shown here. In the flame, there will be what you call vaporized atoms of these elements, and they are emitting light in particular color. Sodium has an yellow color, a particular color. Calcium will have another color. Potassium will have another color, and so on. So why these atoms, when excited, emits particular color? Particular color means a particular wavelength of light is emitted, right? So why this is happening? That could not be explained. Why atoms emit light when excited? They emit light of particular frequencies. One atom may emit a number of frequencies. Another atom may emit a number of other different frequencies. That cannot be explained. Why this is happening, how this is happening, cannot be explained by Niels Bohr. So that's why he modified in 1930. So it is almost 1 century, more than 1 century is over after this model was developed by the young Danish scientist Niels Bohr. Young at that time, youngster. He was actually a student of Rutherford as well. So you can see that a student modifying or rectifying what a teacher has suggested. എന്ന് പറഞ്ഞാൽ അധ്യാപകനെ തിരുത്തുന്ന വിദ്യാർത്ഥി. നിങ്ങളൊക്കെ അങ്ങനെയാണ് ആയിത്തീരേണ്ടത്. We have to correct. Teacher cannot be always be right, because as science develops, we get new evidences. What happens? The earlier theories may have to be modified accordingly or changed accordingly. So that was actually happening here. That point I want to emphasize to you. Okay, right. And now we directly go into the model. Electrons are revolving around the nucleus, that we know from Rutherford model. And Bohr proposed that an electron is found only in specific circular paths or orbits around the nucleus. You can see at the center we have nucleus, then a definite circular path, a definite radius, circular path of definite radius. Electron will be revolving in it. In such a number of orbits of different radii will be present in an atom, right? So just like Earth is revolving around the sun in a particular orbit, we know over a long period there may be slight changes in the orbit of Earth, etc. That is a what you call nuance, or what you call finer details. Otherwise, we can consider Earth has a particular orbit, moon is revolving the Earth, or it will have its own orbit, or you can consider other planets like Saturn, Uranus, or whatever it may be. All other planets you can consider. They will have their own orbits. Similarly, here we have fixed orbits, circular path of fixed radius, and electrons will be revolving in these orbits. And how many electrons can come in one orbit and revolve, etc., etc., details that we come across. This is the main point. You cannot have an electron revolving in any desired path, but in an atom, in a particular, for hydrogen atom, you take, there will be some fixed distances from the nucleus at which you can find the electron. Electron will be revolving in circular path there only, not any desired point. So you can have an electron revolving here, or you can have an electron revolving here. In between these two orbits, we have space. There the electron cannot come or revolve. That is the main point we have to take into consideration, right? So this is our carbon atom. Nucleus, we have 6 protons and neutrons. They are held together by what you call nuclear forces. Then we have electrons. 2 electrons are present in the orbit which is closest to the nucleus. We can call it as first orbit. 4 electrons are in the second orbit. So that will be the electrons arranged in carbon atom. So these are the 2 points we have to take into consideration: fixed radius and energy. Electron, the energy of an electron in an orbit will be fixed. It cannot change. It will be always remains a constant as far as the electron is present in that orbit. If change of orbit takes place, that is another story. We will come across it later. Similarly, its radius is also fixed. That I have already suggested. These are called orbits, stationary state, allowed energy states, etc. They can be named not by different names. We can say that allowed energy state. All energy states are not allowed. Stationary states. That means as far as electron is remaining in that orbit, no change to its energy. Right. Then this is what you call the Bohr condition. Quantization. Quantization means a quantity cannot have any desired value. We have seen the case of energy itself. Energy cannot have any desired value. Energy can have a number of particular values only in an atom. Each orbit is associated with a particular value of energy. Similarly, there is another how we can define the orbits, and this is the major contribution by Niels Bohr. He is not directly quantizing energy. Instead of that, another quantity, it is a circular moment. Electron is having a circular moment, so it will have angular momentum, circular motion, etc. You have studied, we have come across in physics classes. I need not explain it. If there is circular moment, there will be what we call angular momentum. And angular momentum is given by the expression mvr. M is the mass of the particle, v is the velocity of the particle, and r is the radius of the orbit, circular path. That is mvr. That will be the angular momentum of a particle revolving in a circular path of radius r. Right. And this cannot have any desired value. It can have only certain particular value, and that is given by nh by 2 pi. H is Planck's constant that comes in quantum theory of radiation, where energy of a quantum is expressed as E equals h nu. Energy of a photon equals E equals h nu. There comes that Planck's constant itself. Pi is the usual constant we know. N is what you call quantum number, Bohr quantum number. And it can have only integer value. N is equal to 1, you get the first orbit. So, first orbit, angular momentum is h by 2 pi. Second orbit, angular momentum is 2h by 2 pi. That is h by pi. Third orbit, it is 3h by 2 pi. Fourth orbit, it is 4h by 2 pi. Only such orbits are allowed. This is the most important point or postulate regarding Bohr model of atom. This has been developed using de Broglie's equation. We usually pronounce it as de Broglie, but it is de Broglie. That is French pronunciation. It's like that. Okay, fine. And that derivation we did not go into it. How he has utilized this de Broglie's equation to obtain this relation, or utilized that to obtain this relation, that we are not taking into consideration now. But this is the relation, this holds there, and hence we can have only a particular set of orbits. So now the Bohr model is over actually. Then we can have some more points regarding it. Right, fixed radius and energy, okay, mvr equals nh by 2 pi, electron revolve around the nucleus like that. Now, electron revolve around the nucleus in an orbit, no energy is emitted or absorbed. But under certain conditions, electron can move from one orbit to another. Say from first orbit to second orbit, electron is moving. When it absorbs radiation, energy, and it moves from first orbit to second orbit, here lower orbit to higher orbit. And if it comes back from higher orbit to lower orbit, what will happen? Energy will be released, radiation will be released. And the energy of absorbed or released radiation should correspond to the difference in energy between these two levels. So that's why an atom can emit or absorb certain particular radiations only. It cannot absorb any other radiation because electron cannot exist in between these two states. Here we have shown only two states. There can be a number of different states, number of different orbits. Here we have shown only two orbits, right? So electron cannot exist in between them. That means electron can have a particular value of energy. Say, I say for convenience, I say 5 kilojoules, and the higher orbit it is 10 kilojoules. If it is so, so the difference is again 5 kilojoules per mole. 5 kilojoules per mole, I say. Then what will happen? That much amount of energy will be released. 5 kilojoules per mole will be released when the electron moves from higher orbit to lower orbit. Right? That was only an example, not actual case. Actual case, in each atom that it will have a particular energy. I was suggesting only a example. And he also gave expression for the energy which is released or absorbed, as well as the frequency of the radiation emitted or absorbed. Suppose electron is moving from higher orbit to lower orbit, energy is emitted, and the emitted energy is delta E. E2 is the energy of higher orbit, E1 is the energy of lower orbit. The difference is E2 minus E1. We take the difference as E2 minus E1, higher to lower. If the transition is the reverse, what will happen? Then also the difference in energy is delta E is also, but here energy will be absorbed. Electron is moving from lower orbit to higher orbit. So if we can give the electron exactly that value of energy, if you use a photon of that value of energy and you can collide that photon with the electron, electron can absorb it and move to higher orbit. If you give another radiation, electron cannot absorb that. That is it, right? And we can convert it to frequency, simply divide by h. So h nu by nu is frequency of the radiation emitted. E equals h nu. That equation you know, Planck's equation, right? So here the energy of absorbed or emitted light is delta E, hence delta E equals h. And nu will be equal to delta E divided by h, or E2 minus E1 by h. That gives us the frequency or absorbed or emitted radiation. And we can consider this Bohr model energy levels as the rungs of a ladder. Usually ladder we can see that the rungs are at equal distance so that a man can easily climb between. Here it's not like that, we will come to that. And you can see that there are rungs in the ladder. A person can stand on a rung, but not in between the rungs. Right? Similarly, an electron can have in one orbit or the higher orbit, not in between them. Okay. Similarly, the spacing of energy are not equal. In a usual ladder, it will be equal, but here it is not equal. The spacing, as we move up, the spacing comes down and down. It will be less and less. The distance between two levels are high. At the lower level, when you go to higher level, the difference between two consecutive levels decreases. That's true for Bohr model of atom. In hydrogen atom, this will be that point also you take into consideration. So transition happens between these different levels, you get different frequencies from the same atom itself. First to second, you get a particular frequency, or second to first, you get a particular. Third to second, you get another one, and so on. And this is the most important point. Rutherford model could not explain why the elements have been heated to higher and higher temperature give off different colors of light. Now it is obvious. Each atom, the rungs of the ladder is different. The place at which these rungs are fixed is different for each atom. For hydrogen atom, the distance will have particular value. For helium, another value. For lithium, different value, and so on. So for each atom, these values will be different. The energy levels will be different, and hence the difference between the energy levels or orbits also will be different. So Bohr model explained how the energy levels of electron in atom change when the atom emits light. Bohr model could explain that why different colored light can be emitted. Then he approached this quantitatively as well. That we have not gone into. He applied the principles of electrostatics, where as well as circular motion where centrifugal and centripetal forces are balanced and Coulomb's law of attraction etc. were applied, and he calculated, he obtained formulae for the radius of the orbit, length of the radius of the orbit, as well as for energy of electrons in different orbits in hydrogen atom. And that could be checked as well when transition happens between these levels. So that is the next stage application of this Bohr model, how it can be applied, and whether this application is successful in hydrogen atom only or other higher atoms like helium, lithium, etc. That also we have to take into consideration. So that is the next step. For the time being, we stop here. So in the nutshell, there is only one point which should be very clear. We have circular orbits and they are limited by one condition, MER equals NH by 2 pi. That is the key point of Bohr model. MER equals NH by 2 pi. Then if transition happens, energy is emitted or absorbed, and that is given as delta E equals E2 minus E1, and that will be equal to H nu, that is the emitted or absorbed light. So over. These 2 points are clear. Bohr model is over. That is it. Then how it can be applied to hydrogen atom, how it can be applied to other atoms, and how we can quantitatively approach. We need not study the quantitative derivations as such, but the results we have to take, energy equation we have to take. So that is the next stage. We will move on to that in the next class. Thank you. Thank you very much. See you again.